A very good evening. Myself Kirandeep Kaur, Department of Chemistry, Punjabi University, Patiala. Presenting my paper entitled Optimizing Dye-Sensitized Solar Cell with Reduced Graphene Oxide and Macrocyclic Cerium Complex Counter Electrode. Introduction. What is dye-sensitized solar cell? Dye-sensitized solar cells are the next generation of the photovoltaic cells that offers considerable potential because of their multiple functionality, energy-saving capability, and environment-friendly characteristics. There are the various components of the dye-sensitized solar cell: fluorine-doped tin oxide, dye, electrolyte, counter electrode. First, we go with the fluorine-doped tin oxide. Allow the incoming light to reach the photovoltaic layer. Then second component is dye, N71 ruthenium dye, which inject on the induced electron to conduction band of titanium oxide semiconductor. Third component is electrolyte, which is iodine triiodide, which is responsible for the inner charge transfer between the electrode and the regenerate the dye. Fourth component is the counter electrode, which is platinum, which collect and transfer the electron from the external circuit and regenerate the dye for catalyzing a reduction of the iodine to iodide. As the platinum was the expensive material which made device unaffordable, so we can replace it with the efficient macrocyclic complex grafted over a graphene oxide. There are some merits of the macrocyclic ligands, like highly stable, which shows the excellent light harvesting property with strong absorption coefficient and high photocurrent efficiency. Similarly, the merits of the graphene oxide: low cost, larger surface area, and which enhance the property of composite material like tensile strength, elasticity, conductivity, and the excellent electrocatalytic property. Follow the preparation of the graphene oxide by the Hummer's method was followed. For the preparation of the macrocyclic metal complexes, Bush-Biller's method was opted, with dioic compound was refluxed with the dihydrazone and followed by the mixing of the cerium chloride in it. These metal complexes were crafted over the surface of the graphene oxide by the refluxing of the two. In the end, Dr. Blair's method was opted for the fabrication of device in which FTO plates are sintered and applied with the dye and the counter electrode composite and immersed in a dye solution to obtain the final product. Now, in the characterization, first we use the technique. EDS technique was used to verify the elemental composition of the composite. From a figure, it's clear that the synthesized effectively. SEM was used to study the surface morphology of the composite. Here we can see that the composite clearly grafted onto the surface of sheet like surface of graphene oxide. Further, XRD was used to study the proper grafting of the composite on graphene oxide. As the concentration of the composite increases, the despacing value of the graphene oxide will decrease, which reveals the proper grafting of the material. To check the photovoltaic characteristics of the material, IPCE curve was obtained. The different composite was examined under a same wavelength as dye was used in all samples, that is 540 nanometer. The data showed that as the concentration of the metal composite increased, the IPCE value reaches to the maximum value, 85%. That is even higher than the traditional platinum. The other parameter used was the current density voltage curve, which revealed that the efficiency of device raised with the increase the concentration of the macrocyclic metal composite over a graphene oxide. Here from data, we can see that the composite with 1:10 exhibit the maximum efficiency 8.05%, followed by the traditional platinum counter electrode. So here we conclude that these composites were utilized under a physical, microscopic, spectroscopic analysis, including the SEM, EDX, XRD, to confirm the successful grafting and understand the material properties. Second, the transformation of the graphene oxide into reduced graphene for the efficient counter electrode in dye-sensitized solar cell, contributing to the advancement of the renewable energy technologies. The incident photo to current efficiency curve showcased a remarkable increase in the IPCE value with the each incremental rise in the concentration of the macrocyclic metal complex. Particularly, the counter electrode with 1:10 configuration exhibit a superior performance. The cerium doped graphene oxide 1:10 configuration demonstrated the highest short circuit density and open circuit voltage values among all the tested ratios, even outperforming the platinum electrode in the certain instances. Favorable catalytic efficiency of copper played an essential role in the accelerating the reduction of the oxidized dye, contributing to enhance the electron transfer and resulting in higher short circuit current density. The redox capacity of the copper, coupled with its ability to undergo a oxidation and reduction reaction, further contribute to the overall efficiency of the solar cell.
Yes.
Thank you, ma'am.
Have you completed?
Yes, ma'am.
Okay.
Yes, ma'am. Good evening. My name is Aman Kumar, PhD scholar in NIT Agartala. Today, my topic is the photonic crystal fiber based refractive index sensor and approach of biomolecule testing application. Under guidance of Dr. Nomita Goswami, Assistant Professor NIT Agartala, and Professor Arjendu Saha, NIT Agartala. These are my outlines, and this is abstract. And in this simulation, a model has been developed to create the fiber core with with an analyte refract surrounded by high sensitivity and the surface utilizing photonic crystal fiber. This sensor employ a combination of the perfect match layer, enhancing sensitivity by the refractive index from 1.30 to 1.40. Over a wavelength range of 14 nanometer to 10-16 nanometer. Photonic crystal fiber. Uh, Regular structure fiber such as photonic crystal fiber have the cross section consisting of the one, two, or more materials most commonly arranged periodically over match the cross section. This the zone is known as the cladding. Cladding and is surrounded a core where the light is confined. For example, the fiber first demonstrated by the consisting of the hexagonal lighting of the air holes in a silica fiber. This is my proposed scheme. The cladding the refractive index is the slightly lower than the fiber core due to the organization and the presence of air of aperture within this year. The feature of the air holes with the diameter of all air hole diameter is the 0.76 micrometer, and the first layer is the fused silica is used, and the second is next is the used next is the used layer is the analyte, and the last is the perfect match layer. This is equation is used in first Selmer equation in the refractive index of the silica core. Lambda, where lambda is the wavelength is the micrometers, and the B1, B2 is the B3, and C1, C2, C3 is the Selmer coefficient. To observe the radiation energy and improve the computational accuracy, the perfect match layer in the artificial, the calculate confinement loss by the equation where lambda is the operating wavelength in the micrometer and imaginary and effective refractive index. This is the output of the fundamental modes in the electric field distribution X and Y core modes. Sensor has the two fundamental modes, the X polarization and Y polarization due to the phenomenon. These X polarization and Y polarization fundamental core guided mode for this structure where the cross horizontal and the Y component is the so higher loss as well as the higher sensitivity. So here Y component is the fundamental core mode. Core mode is regarded for the following work. This is my output. Wavelength confinement loss with respect to wavelength. Uh, First of the 1.302 increase the 1.31 increase it to 1.40 analyte refractive index, and the confinement losses of the design the sensor depend on the refractive index with different refractive index. This is conclusion. This study the interview but practical SVR sensor utilizing a PCS structure design the accurate de- detection of the external sample. The biosensor demonstrated exceptional performance metrics, including the maximum wavelength sensitivity of 1625.9 dB RIU with a resolution of the 9.68 into 10 to power minus 6 RIU. The summary, the non-uniform core refractive index distribution induced more property changing has been studied. Fluctuation of core refractive index can be caused mode, shape, and distribution. Thank
And
you.
I'm working as a Prime Minister Fellow at CSIR, CSIO Chandigarh. I'm working on the sensing of heavy metal ions in the water using the electrochemical techniques. And in this recent research, I have worked on the cadmium detection using the modified gold electrode with the platinum nanoparticles. That is a highly sensitive voltammetric platform for heavy metal detection. These are the outline that I will cover today, starting with the introduction, then literature survey, research gaps and novelty, objective results and discussion, conclusion, references. So the problem statement is the cadmium toxicity, that is the natural occurring heavy metal found in rocks, soil and coal. Also, it is found in the cigarette smoke, also released from the industrial processes, etc. So from the different sources, it entered into the water bodies, and through the water bodies, it accumulate in the body over time, and its exposure can damage the kidney, lungs, bones, even leading to cancer. So in the recent study, I have addressed this problem statement of the cadmium toxicity. So to monitor the cadmium ions, I have selected the square wave voltammetry. That is a powerful technique for the cadmium detection because as per the World Health Organization standards, cadmium safe limit is 5 parts per billion. So to trace up to such lower limits, square wave voltammetry is the selective and sensitive technique. So the main motive for this study is to rapid detection of the cadmium ion to ensure the immediate action to minimize the exposure and help safeguard public health by ensuring water supplies are safe. Also to help to track cadmium levels in the environment to identify the potential pollution source and prevent future contamination. As per the literature search, different rivers, districts, states are suffering from the cadmium ion toxicity. So the research gap I found is while detection limits are improving, but there is some regulation that have extremely low threshold. So there is a need of further optimization of the electrode material by utilizing advanced material or exploring new material to enhance the sensitivity of the sensor. Also, in the environmental or real water samples, there are interference also from the foreign ions in the real sample. So there is a need to develop anti-interference strategies. And the novelty of the work is in the work I have used the platinum nanoparticle that have a high conductivity and can act as efficient catalyst, facilitating the electron transfer between the cadmium ions and the electrode that lead to faster response times. And also in the study, I have addressed the crucial aspect overcoming ion interference issues that are commonly faced in the real world water samples. And so the combination of the square wave rapid analysis with the high sensitive platinum nanoparticle, making the sensor promising for on-site and real-time detection for cadmium contamination. These are the objective of my recent research to synthesize the platinum nanoparticles to enhance the sensitivity and selectivity of the sensor, then to detect the cadmium ions in water using square wave voltammetry, then to calibrate and evaluate the limit of detection, and then to study the interference effect using real water samples or foreign ions. These are the methodology principle of square wave voltammetry. It is based on the principle of the redox reactions. In the square wave voltammetry, there is a setup of 3 electrodes in which the main row play the working electrode. When we apply the reduction potential, the ions present in this solution deposit on the surface of electrode, and after some time, these deposited electrodes get back into the solution and release electrons, and these electrons generate the current peak. So from the height of the current peak or current signal, this is directly proportional to the concentration present in the solution. So first I have synthesized my platinum nanoparticles and drop cast it on the working electrode of the gold and enhance the surface area of the electrode to increase the sensitivity and selectivity of the sensor for particular cadmium detection. For this, I have optimized the different electrochemical parameter, among which the first is the deposition potential. At particular deposition potential, the ions present in the solution deposit on the electrode surface. So for this, I have taken data 0 to minus 1.1 volt, and among them, I found
Please wind up within 2 minutes.
Okay, ma'am. So I have optimized the parameters, and after optimizing the parameters, I have got the linear curve for the concentration 0.1 to 0.5 micromolar and got the linear curve with the sensitivity 30 micro ampere per micromolar. So using the equation, we can calculate the concentration of the unknown sample of the real water samples. I have also tested the repetition study. For this, I have repeat single sample 5 times and confirm the stability of the sensor. Also, I have for the interference study, I have taken the Panipat region, Haryana real sample. That is a textile hub where large number of industries are running, and in the literature there is a presence of the cadmium ion. So among 27 collected samples of the Panipat region, 15 was found cadmium concentration. And also in at lab scale level, I have taken the different foreign ion like fluoride, iron, nitrate, copper. So using these interference, my cadmium signal is not affected, so the sensor is free of the interference. So as per the conclusion, I have taken the range for the cadmium 0.1 to 0.5 with the sensitivity 30 microampere per molar, r square 0.9 square, and using this sensor I detect the cadmium ions up to the limit of 4.67 parts per billion. These are the reference I have used. I would like to acknowledge CSIR, CSIO, Gram Bharati Mahavidyalaya Ramgarh, and FICI, that is my funding firm. Thanks to all.
Namaskaram, and thank you for this online platform to present my work.
How many slides you have?
Exactly 10 slide, ma'am.
Exactly. Please continue.
Yes. Yeah. So here I am Yogesh Chaudhary, and from CSIR IMMT, I'm working as a PhD research scholar under the guidance of Dr. Kamachi Jyoti Ramalingam Sankaran. And today the talk will be dealing about the fabrication of diamond graphite electrode for electrochemical sensor for the detection of toxic paraquat. So in this talk, I will mainly discuss about the toxic effects of pesticide, paraquat pesticide. Then after we will go for the characterization, and we will go synthesis, then characterization, followed by the electrochemical study. So now, are we really the prey of toxic pesticide? Yes. We see, we have breaking news that 44% of farmers and farmer workers are globally poisoned by pesticides, and it's reported by BBC and the other Indian Express News also. Not only from the crops, we can also observe that the spices also contain the pesticides. So these pesticides are really toxic to us, and how they are incoming throughout body. So when they are getting inside the agriculture through the ingestion, inhalation, and skin contact, it may affect to the humankind, and the impact will be the acute as well as chronic. And not only this, it also affect the reproductive parts of the reproductive health organs of the human, like it may cause birth delay and miscarriage. So we have the responsibility to protect our children before our birth also. So we should get protected from toxic pesticides. So it needs regulation methods, monitoring techniques. So what are the techniques? What are the techniques that we have? And conventional. So conventional techniques like liquid chromatography, high performance liquid chromatography, gas chromatography, these are all conventional techniques that were used for the detection of pesticides. Now, what are the drawbacks of these pesticides? The complicated instrumentation, it takes space and it's time consuming. It's very tedious sample preparation, and this is unsuitable for the on-site analysis. So now we want an alternative, that is electrochemical sensor. Why? This is due to its great characteristics, like it is low cost, fast response, it has a low detection limit, portable, the most important thing, and the highly selective and easy to operate. But how it is working? Just for example, an analyte maybe like Miss Monika, she was telling about cadmium, that may be analyte, and here for this, for me, it's a toxic pesticide like paraquat. So when it gets contact with the electrochemical sensor, it gives a sensing signal that is converted by transducer and giving a peak shape voltammegram. So if there is peak shape voltammegram, we can say, it is detecting. So now then for detecting, we need electrode. So previously, most of the literature shows the graphene-based electrodes are efficient, but actually they have high surface area, electrical conductivity, and flexibility. But this graphene electrode have some prominent drawbacks, like inconsistent in electrode fabrication and unsuitable towards oxidizing agent. Complex functionalization, aggregation is the main problem. Surface falling is also. So how to overcome these drawbacks? So in order to overcome these drawbacks, we use diamond-based electrode. Diamond-based electrode has highly chemical stability, and it has a wide potential window, and its background current is also very low, and it is biocompatible. Mechanically, it is robust, and also it is resistant to falling. But however, it has also wide band gap. So we thought, why don't we mix a graphene and diamond so that we can get a hybrid of diamond graphite? So our motivation was that the fabrication of conducting hybrid diamond graphite electrodes, this is just a synthesis of a single step, just by varying the concentration of methane in this plasma. So, and then after we have to go for TEM analysis for study the microstructure, and then finally the electrochemical study for toxic paraquat. Now, the question is how diamond electrodes are grown. So we can say that this is a single step synthesis by using the microwave plasma enhanced CVD, chemical vapor deposition. So the growth condition is that we have to vary the methane concentration while keeping the hydrogen and nitrogen as constant by applying the microwave power of 3000 watt and the pressure under 65 torr silicon substrate. Here we can see on silicon substrate, the microplasma, due to the microplasma, the thin films are grown of hybrid. So then after we use this, we actually from this growth system, we have developed 4 different samples by varying the concentration of methane from 1%, 5%, 10%, and 15%. So we have seen while increasing the concentration of methane, the granular diamond is getting converted into nano needle-like structures. And then after we used the electrochemistry to characterize the synthesized electrodes, and for that we used the CV cyclic voltammetry, and we have done the cyclic voltammetry of 4 different samples. And from this CV we can claim that the 15% methane sample is showing better peak current, and similar it is supported by differential pulse anodic striping voltammetry. And from this also we can clearly see the NCD 15% is showing better peak current in comparison to other electrode. And so what we can claim here, the higher the peak current of the electrode means the higher the greater the redox active efficiency. And then in support of these two, CV and DPSP, we perform EIS, and EIS has also shown the charge transfer resistance for an LCD 15% sample is very low in comparison to other 147.7. Then from this characterization, we saw that LCD 15% is showing better electrochemistry than we did for the characterization in order to do whether the graphitized or not. For that, we have to check for Raman. So from the Raman, along with all the characteristic diamond peaks, we obtained the characteristic 2D peak in NCD 15% means nanocrystalline diamond, which contains 15% methane. So characteristic peaks are observed, and we can say from the Raman that it is graphitized. And from HRTM also, we can clearly see that this is the magnified image of A, where we can see that the diamond, this fringes, and here the graphitized fringes. The graphitic phases are also present in the grain boundaries of diamond. Here, from this pattern, dark field pattern, we can see that the yellow colored needle-like structures is of diamond, and which is encapsulated by the graphitic phase that is shown in the green color. So here we have seen from this HRTM, we have confirmed that the graphitized hybrid graphitized diamond electrode is synthesized, and this is responsible. This graphitic carbon is graphitized electrode is responsible for the high charge transference. Then after we used for that electrode, that NCD 15% methane sample used for the paraquat detection, and for paraquat detection we vary the concentration from 0.1 micromolar to 0.8 micromolar using the differential pulse and anodic strapping voltammetry. And what we have observed, if there is no toxic paraquat, there is no peak current, but while increasing the concentration, the peak current is increasing proportionally. And this is done at optimized condition of having the electrolyte 0.1 m phosphate buffer solution of PS6, deposition potential, and this. The data for the optimization that I have not shown here, but it is optimized. And now, after plotting this peak current versus paraquat concentration, we obtain the linearity.
Please wind up with 1 minute.
Yes, the linearity shows that this is 0.002 micromolar LOD, which is far below than the reported WHO. Now, this is the reported literature that shows our LOD is far better than other reported electrodes for paraquat detection. Now, in order to study the selectivity, we used different ions and interfering agents, and in presence of all these, we got paraquat has similar peak current. Similarly, for reproducibility, we use 5 electrodes, and all these are similar peak current. Similarly, for repeatability, we use up to 50 cycles, and the peak currents are almost similar. And we use 50 days for the stability test, and the relative standard deviation is around 11. Not only that, we have done the real-time study for seawater. We applied and we obtained the limit of detection 0.02 micromolar. And for amaranthus leaf, what we use in our daily life, there also we have applied this peak current. So now the summary is that we have fabricated the hybrid graphite electrode, and then that is applied for the paraquat detection, and from the linearity, we have calculated the limit of detection, and this is also showing the highly selective, excellent reproducibility, and highly durable. And for the further work for this work will be the development of prototype electrochemical sensor. And this is submitted. Thank you, one and all. Thank you for your kind patience.
Good evening to the session chairs, respected researchers, and all my esteemed attendees. I'm Aman Kumar Jha from Department of Electronics and Communication Engineering of Institute of Engineering Management, Kolkata. Today, I'm here to present my paper on modeling of nanosensor device for evaluating electronic interaction with nitrogen dioxide pollutant, combining multiphysics approach and DFT study. Moving on to the introduction of this paper, 1D nanostructured materials, especially like nanowires, nanocoms, which have a very high surface to volume ratio, are known to have excellent chemical and thermal stability. And that is the reason it is of a very high interest for researchers who are working in the field of environmental monitoring, medicine, and other gas sensing technological fields. Among all these materials, zinc oxide stands out different. It has a unique wide band gap of approximately 3.3 electron volts, which is very much suitable for application in solar cells, chemical sensors, and flexible electronics. Nitrogen dioxide is a very notorious harmful pollutant which causes very severe respiratory and cardiovascular diseases, especially in children. Therefore, in this study, we are progressing with an aim to create a zinc oxide nanowire-based device model using COMSOL multiphysics software and Gaussian software for performing the DFT study in order to evaluate the chemical response of the zinc oxide nanowire towards NO2 pollutant. Now, the primary objective of this paper is to design such a sensor device model and evaluate its chemical response. Second, to understand the electronic interaction and change in properties and the mechanism how nanowires actually change or behave with the exposure of NO2. Then to investigate nanowire as an effective candidate for gas sensing and for further broader applications in nanotechnology. The novelty of our work is that we have combined multiphysics simulation and DFT analysis to provide an in-depth understanding, and also it highlights the potential of nanowires based on zinc oxide for environmental monitoring and pollution control. Moving on to methodology, how have we achieved it? In COMSOL multiphysics, we have used a silicon substrate for mechanical support, over which there is a zinc oxide-based seed layer, which will serve as an experimental platform. Then we have hexagonal cylindrical zinc oxide nanowires, and then we have two symmetrical tungsten electrodes over it. Physics-controlled meshing was used via the electric currents module in COMSOL multiphysics. In the Gaussian and Gauss-View calculation, the entire thing was performed in the ground state using the PM6 method for optimization of the geometry. An extended quadratic convergence algorithm was used to ensure reliable and stable convergence. When now we move towards the results and discussion, the first thing which comes is the study of electric potential of zinc oxide-based nano device. We applied a differential input of 5 volts on the right electrode and onto the left electrode. This differential input was found to be mostly strong just beneath the electrode in the nanowires. In both the cases, we can observe, which I can show you using a pointer, just a second, yes, that just below the 0-volt electrode, which is set at 0 volt, we can see its maximum effect, and then gradually the potential increases and then again reaches its maximum under the right-hand side electrode, which is at 5 volts. This forms a distinctive U shape. Moving on to the next, single nanowire electric potential and current density simulations. Like the nano device, single nanowire also exhibited that gradual variation in its electrical potential from top to bottom. But in the case of uniform current density, we found something strange. We found that even though the current density is predominantly uniform in the entire structure, there is some irregularities, there is some non-uniformity near the top surface. Now, why it is this? It is because at the boundary or the interface of any material where the gas is going to be absorbed, the effect of electric field on the electric potential are most strong. Therefore, when a bias voltage is applied to the top of the bottom faces, it significantly modulates the localized carrier concentration and mobility, which we can observe by the current density variation. Moving on to our DFT calculations. Study of molecular orbitals of zinc oxide nanowires. Before NO2 interaction, we found a HOMO-LUMO energy gap of 0.074 electron volts. But after, when it was exposed to nitrogen dioxide gaseous environment, we found that its molecular orbitals got divided into two different parts, alpha MOs and beta MOs, and its energy gap increased. It increased in alpha MOs case to 0.144 electron volts, and in case of beta MOs to 0.135 electron volts. Now, then we moved on to the electrostatic potential plot of zinc oxide nanowire. Before NO2 interaction, we saw that in the middle section of the nanowire, we can see rich red region. Here, red represents electron-rich regions and blue represents electron deficit regions. We can see a clear demarcation between those two regions. It's because The top and the bottom surface of a nanowire is the place where the gas is going to be absorbed. So that is the place which have dangling bonds, which have defect states, and that is why it has electron deficit. Whereas in the central part of the zinc oxide nanowire, we see that there is complete stability and electron-rich regions are present. After NO2 interaction, in the right-hand side of the slide, we observe something different. We see that the entire electron deficiency and electron richness slightly weakens, and the entire nanowire tends towards a neutral state. That can be represented using yellow and green color. This was also further verified with our previous HOMO-LUMO slide, where we also saw that the energy gap was increasing after interaction. Energy gaps increase means that the entire structure is moving towards a more stable configuration.
Excuse me, Mr. Aman, please summarize.
Yes. Now, in our conclusion, we actually monitored crucial parameters like potential, density, and HOMO-LUMO energy gap and ESP plot to find out the sensor sensitivity and selectivity towards NO2. And we found out that yes, zinc oxide nanowire not only just respond to it, but significantly responds to the nitrogen dioxide gas when it comes in its contact. This research not only just does that, it advances our also comprehension of how electronic properties and behavior of ZNO nanowires changes with adsorption of different gases. For this research, I would like to also acknowledge the support of the EC department of IIM Kolkata and Shobana Chatterjee, Shovik Bhanja, and Siddharth Bhattacharya, who has provided some really helpful inputs. Thank you for your time, and now I'm open to any questions.